Yes. Okay. Last day, we were looking at, and I just wanted to finish graphite because we had almost made it through graphite and then we ran out of time. So when last we left, we had carbon attached to carbon in a hexagon pattern, which means that every carbon has how many electron domains? How many electron domains? 3. Okay. 1, 2, 3. Which means what is the geometry? Trigonal planar. What's the bond angle? 120 degrees. Now, what type of bond is a single bond? That is a sigma bond. And when we have a double bond, we have a sigma bond plus a pi bond. What kind of overlap results in a sigma bond? Head to head. Head to head. Yeah. And what kind of overlap results in a pi bond? Side by side. Oh, and look, do you see the symbol pi? It's got these two things. Yes? Okay, pi bond. So what you have is you have electron density. If we were to draw our electron density for a single bond, where would it be? Where is the electron density? In the middle. It's along the internuclear axis. Sigma bond. What if we have a pi bond? Where is the density? Top and bottom. So both those lobes together make one pi bond. Okay, and if you had a second pi bond, what would you have? If you had a sigma bond and 2 pi bonds, what would you have? You have a triple bond. So the pi bonds are here and here, right? Where would my second set of pi bonds go? Yes, top and bottom, front and back. Yeah? Okay. Now, we were looking at the entire structure here, and we were looking, and do you see how we are alternating single bond, double bond, single bond, double bond, single bond, double bond? Yes? And that's going to happen in all of these. Yes? I've done something wrong. What have I done wrong? I think it's this one. Yeah. I don't know what I've done wrong. Anyway, doesn't matter. I've done something wrong. When you have, it should be, anyway, I don't know. I don't know what's wrong. Anyway, when you have these alternating single double bonds, what can they do? They can form a ring thing. Just like, do you remember benzene? I'm just going to draw benzene because it's easier to see, because this is like really complicated and yucky. Okay, so here is benzene. And if we have a double bond here, here, and here, this double bond can move so that we have single bond, double bond, single bond, double bond, single bond, double bond. Is that ringing bells? Yeah. Yes. What do we call this process where it goes back and forth? Pardon me? Resonance, yes. Okay, so that is a resonance structure. So when you get that flipping back of where, like that moving around of the double bond, that's called a resonance structure. Now, is that actually what happens? Do we actually have the electrons going bing, 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 like windshield wipers? Back, forth, back, forth, back, forth. No. What do they do instead, for real? They kind of smear over the whole area. Okay, so what we're going to do is we're going to take this electron pair, this electron pair, and this electron pair. How many electrons is that? How many electrons in those 3 pi bonds? 6. We have 6 electrons, yes? Yeah. Okay, and we're going to spread them out across 6 places. So each sigma bond has 2 electrons, yes? And then we're taking these 6 electrons and we're spreading them out over the 6 bond areas. So in essence, you would never ever draw it like this. What is wrong? Where are you not erasing? Come on, there we go. You would have electron, 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 but we never draw it like that. Okay? What we would do, I'm just going to put this in brackets, do not draw this. How would we draw it? Yes? We draw a dotted line, okay? Is good? Okay. And what is the bond order? Bond order is 1.5. Because a single bond order is 1. Double bond order is 2. Triple bond order is 3. So if you have 3 electrons in that area, you have 1.5. Yes? Now what if we had something where we had like that? That would be a 1.3 bond order. Yes, because we would get resonance, like let's just say this is a negative here. Okay, 2 negative. It would resonate here. Oh, I'm making it carbonate. Look at me make it carbonate. Okay. Yes? Yes? Yes, this is an ion. Okay, and I haven't drawn on any of my lone pairs. You're like, where is this coming from? Yeah, these are ions. Okay, so we have 3 resonance structures. So this is going to be a bond order equals 1 and 1/3. Okay, or 1.33. Is good? Okay, now we have this resonance. So what can you say about these electrons? Are they localized or are they delocalized? The pi bond. The pi bond is delocalized. When you have resonance, the pi bond is delocalized. And why is this important for electrochemistry? Which is why we're doing this right now, because we're talking about electrochemistry. Yes, we are, I promise. Why would it be important that in graphite, back to graphite, why would it be important that we have delocalized pi bonds, delocalized electrons? And what could we have? What could be happening here? Here, let's make them move in red. We have electron movement, and if I put a positive terminal over here, the electrons are going to move that away, yes? Or that away, sorry, I'm backwards from you. And if I put a negative terminal over here, they're gonna move away from the negative terminal and towards the positive terminal. So what can happen is graphite can conduct electricity in the plane of the hexagons, yes? It can conduct electricity this way, but not this way. Does that make sense? Because within this structure here, we have those delocalized electrons within that plane. So what you would need to do is you would need to have a piece of graphite where all the layers were like lined up this way, and you can make something that sticks into a half cell. Do you remember what it's called? It's usually made of a metal, but it could be made of graphite. An electrode, we can make an electrode out of graphite. Electrodes have to be either a metal or they have to be graphite so that they can conduct electricity. And we spent all that time talking just so we could remember that graphite can conduct electricity. Yes? Yes, you can, absolutely. In fact, there are little labs where you take a pencil and you snip off you like sharpen both ends and you can actually make an electrochemical cell with it. You can use it as an electrode. Yeah, right? And if we had like more time, we would do that, but we're not going to have enough time. I'm so sorry. Okay, anyway. Okay, so that was all that. Now let's go back to actual electrochem. And did you have any questions from 6.3a? Were we good? Okay, let's move on to 6.3b. Yes. Ah, okay. Here, let's go see. Why would we use 2 beakers for number 5? We would use 2 beakers because if you were to take, let's go and look up and see which one we have here. We have nickel and chromium. So nickel is, where's nickel? Nickel. Chromium is here. And nickel is here. So we're going to get a spontaneous reaction that way. So if you have 1 beaker with nickel ions in it, and you have a chromium electrode, and you have a nickel electrode, and let's say we also have some chromium ions in here. Okay. Now, nickel 2+ is going to react spontaneously with chromium, yes? So, if I join this with a wire, is there any incentive for the electrons to pass through the wire, or can those electrons that are in here just grab onto the NO2, which is right beside it because it's in solution? Yeah. So that's why we need to actually separate the nickel 2+ from the chromium electrode, because otherwise they'll just be like, oh, electrons, hello, thank you, I'll take you, and they won't go through a wire because it's the path of least resistance, right? Going through a wire, there's more resistance in a wire than there is just having the ion floating next to you. So that's why there have to be 2 beakers. Yes? Electrolytic cells will work because you're never going to have that spontaneous process. If I'm chromium metal, I'm like busy giving off my electrons. I'm like, here, have some electrons. Nickel, here, have some electrons. Nickel, you know, that kind of thing. But in an electrolytic cell, what you will have is you will have 2 things sitting there, and they don't want to react. They are non-spontaneous. So in an electrolytic cell, what we might have is we might have in our beaker the chromium and the nickel, but we would put in here only Cr3+. So now I've got Cr3+. We're not going to put any nickel 2+ because then we'd get a spontaneous, like, just reaction within there and no wire is necessary. We now have chromium 3+ and nickel, and that is a non-spontaneous reaction, yes? So you're not going to have chromium 3+ going up and grabbing electrons from the nickel electrode. It cannot do that. But if we attach a battery and we say, here's my, let me make sure I'm putting the battery the right way around. Nickel is losing electrons. Chromium is gaining electrons. Nickel is losing electrons. So my electrons are going this way. I always like working with electron direction. So if my electrons are going that way, my positive terminal has to be here. My negative terminal has to be here. Right? So now this battery up in the wire, like attached in the middle of the wire, is forcing electrons out of nickel and into chromium. At that point, chromium 3+ can go to the chromium electrode and plate onto it. Yes, and grab those 3 electrons that are being pumped into the chromium. Does that make sense? Cool. Other questions? Yes. No.
You make a battery out of like a different, it just is a solution.
A battery is basically an electrochemical cell, a galvanic cell, but we take the beaker, and instead of having a beaker full of liquid, because that's not going to work very well, you know, sloshing around, we make it into a paste. Okay, so we have a paste. Ions can still move in a paste. Okay, and we also make a paste out of our other half cell. We still have the metal and the metal, and we have a paste and a paste. And then we smush them together. We make a cylinder out of one. We make a smaller cylinder out of the other. And we attach them. There's a salt bridge in between, which we'll learn about today, what a salt bridge is and why it's necessary. Okay, and we smush them all together and we make a battery. Yes. So a battery is basically one of, where did it go? Oh, don't want equilibrium, electrochemistry. A battery is one of these. We've just pastified the liquids. Yes, we've cylinderized everything so it all fits in like into a nice little, you know, D cell or whatever. And yeah, that's it. Yeah. Is good? Okay. Let us hang out with Tyler then today while we go a little bit deeper into galvanic cells. What are the three names for galvanic cells? Excellent. Okay. Here we go.
In this video, we're going to talk about galvanic
Why is there no
cells,
sound?
which are also called cells. So what are they?
Hang on.
Well, galvanic or voltaic cells are devices that use a chemical reaction to create electricity. Specifically, the type of chemical reaction that they use is called an oxidation-reduction reaction. But we'll talk more about that later. Now, galvanic...
So we are on page 69. If you're looking for what page we are on, devices that use a chemical reaction to create electricity are what galvanic and voltaic cells are.
Galvanic or voltaic cells may be totally new terms for you, but I'm willing to bet that you use these devices almost every single day of your life. And that's because a battery is an example of a galvanic or voltaic cell. There are chemicals inside batteries, and those chemicals react together in an oxidation-reduction reaction that makes electricity. And this is what powers your cell phone or your flashlight or whatever the battery is hooked up to. So let's learn more about these devices and see how a chemical reaction can create electricity. Okay, so I think for the rest of this video, I'm just going to call these voltaic cells instead of calling them galvanic or voltaic cells. All right?
Or electrochemical.
So I now want to talk about the parts of a basic voltaic cell, one that you could actually make in the lab.
So you may be called upon at some point to draw an electrochemical cell, so you should know the components that make it up, okay?
So here's what they are. First, we start with two beakers or containers of water. And into one of them, we dissolve some zinc sulfate to make a solution. And then into the other, we dissolve some copper sulfate and make a solution with that. So we got these two solutions. Then we take a piece of zinc metal, like
What's that called? The electrode, yes.
this one right here, and put that in the zinc sulfate solution. And then over here, we take a piece of copper metal and we put that in the copper sulfate solution. The next thing we do is we take a wire, a metal
Page 70.
wire, and we use that to connect the two pieces of metal together. And when we do this, something amazing starts happening. Electrons start moving through this wire. They move from the zinc metal into the copper metal. Now, this is a big deal because moving electrons are what make electricity. So when we hook this wire together with the pieces of metal and electrons start moving through it, we have electricity. We have electricity moving through this wire. And what we could actually do is we could take a little light bulb like this and hook it up to this wire, and the light bulb would turn on because there's electricity moving through this wire. Now, to be really specific.
Now what I want you to notice is I want you to notice that the electrons are moving. So they start here in the zinc. The zinc gives up 2 electrons. What does it become? Zinc 2 plus, and you'll end up with a concentration greater. The concentration of Zn2 plus will become greater over time. And the electrons move over here, la, 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 la. And what happens to the copper 2 plus in solution? It grabs those 2 electrons. Now, as time is going on, what would happen to the charge of the solution in this beaker? It would become positive. What would happen to the charge of the solution in this beaker? It would become negative because you're using up positive ions, yes? Does nature love a charge imbalance? No. So if you actually set this up, the light bulb would not light up because the electrons would not flow towards a negative area. You cannot have a buildup of charge on one side. You need to maintain electrical neutrality in both containers. And if you think about it as like in physics, you know, when you have a moving charge, what do you need? You need a circuit. You need a complete circuit. Right now, is that a complete circuit?
No.
That is a half circle, yes, at best. All right, so let's see how we actually complete that circuit.
There's one more part of the voltaic cell, and that's a little tube called a salt bridge that connects these two solutions.
What do you think is in the salt bridge? Salt. What state do you think that salt is in? Is it going to be solid or is it going to be aqueous? Now let's think about this for a second. We have electrons, negative charge, moving this way. What do we need to complete the circuit? If I've got negative charge moving this way, my electrons are moving this way, what has to happen here? What do I need moving this way? Ions, right? Can solid ions move? No. So what kind of salt do we want in our salt bridge? We could have liquid, but you would have to melt some salt, and that's like not particularly easy to do. Plus, it might be hot enough to melt the glass of the tube, which is also not so easy to do. So how could we make those ions mobile without melting the salt?
Water.
We could dissolve them in water. So this is going to be an aqueous salt. And if the electrons are moving this way, what will be moving through the salt bridge this way? What kind of ions will be moving that way? Electrons go here. What goes this way? Negative ions. Can the electrons move through solution? No, electrons cannot move through solution. They do not dissolve into solution. What happens to the electrons when they get over here? Do they jump into solution or do they do something else? They grab onto a copper 2+ and become copper solid. So it's not like those electrons are going anywhere after they make it to this electrode. They're just grabbing onto copper and becoming copper 2 solid. Okay? So we need the negative charge to keep flowing this way. So our negative ions are going to move this way. What do you think happens to the positive ions? Sorry, yes?
So wouldn't the copper all solidify and then wouldn't have any ions to move that way? Or are we like introducing different ions?
In our salt bridge, we're putting a different salt, probably something unreactive. Yes, because we don't want, I wouldn't want to put, say, what precipitates with copper? Let's say I put sodium hydroxide in here. Hydroxide will precipitate with copper, or actually it'll precipitate with zinc over here. So if I had hydroxide in the salt bridge, it would come over here and it would precipitate the zinc. That would be a sad state of affairs, yes? We don't want that. So we're going to pick something nice like potassium because it is a alkali, or sodium because it is an alkali. Will those precipitate with anything? No. What would be a good choice for our other ion? Our anion. Nitrate, because it doesn't precipitate with anything. In this particular case, because sulfate is soluble with zinc and copper, you could also use something like sodium sulfate or potassium sulfate. But you would have to check. Nitrate is always a good choice because it doesn't precipitate with anything. Is good? Okay. Don't worry, we'll come back to the salt bridge more later. Yes? Well, feel free to ask away. Yeah?
How you connect two aqueous solutions with an aqueous solution?
Oh, basically what you do is you take, it's like a little U tube. Okay, so it looks like this. Let's see if I actually have one. Okay, just give me a second. You know what we're going to do? We're just going to take a little break from Tyler for a second. I don't know where the things are. So we're going to look and we're going to go. Demonstration. Oh, there we go. Okay. You need two L's to be a
In this
Daniel.
experiment, we want to build a galvanic cell, more particular, a copper zinc cell, or also diamond
I've not
cell.
previewed this video.
We use two metal sheets as electrodes. On the left-hand side, a zinc sheet, and on the right-hand side, a copper sheet. Both are connected to the voltmeter. Zinc is then put into the zinc sulfate solution and copper into the copper sulfate solution.
Let's see what voltage we get. What voltage do they get?
The zinc oxidizes. Zinc ions enter the solution, and electrons remain on the sheet.
Lying.
These electrons go down the wire to the
You're
copper
lying. It doesn't happen. What does the voltage
metal.
read? 0.
If we
Oh,
connect-
look, you know why it reads 0? Because we don't have a salt bridge. Now
Because
she's
we
going to
still
show us a
need a
different
salt
kind of
bridge
salt bridge here.
that is dipped into sylvite.
Oh, potassium chloride.
If we
she said
connect
sodium.
both half cells with the dipped paper towel, a charge equalization takes place and current flows.
So this is rather than
If
using
we
a
remove
YouTube,
the
you can use a
salt
paper
bridge,
towel
the
soaked
charge
in
equalization
the
stops,
solution.
and so does the
See how we get a
current flow.
voltage now, and the voltage goes away because we're allowing movement of the ions. So that's one way of creating a salt bridge, a really cheap and easy way
Not
of creating
only
a
the
salt
salt
bridge.
bridge is essential. The two metal
Now,
sheets
just
have
before
to
we-
be in their solution to make
We're not
the
going to carry on with that one. Let's see if we can find one that has an actual glass U-tube. Oh, this one has a glass U-tube. Here we go. Oh, but you're not allowed to argue Le Chatelier on the AP exam, so pretend you heard nothing. Okay, let's just go and look at the YouTube. There's the YouTube. Can you see it? Let's make it bigger. Do you see what we have in either end? What's that? That is actually a cotton ball. So what we do is the YouTube is like this. We fill it up with the salt solution, and then we put a cotton ball on each end, and then we just flip it over and stick it in the beaker. Okay, and the stuff doesn't drip out because it's got the cotton ball in the end, but ions can pass through that cotton. Is good? Cool. All right. Let's go back to Tyler now.
Talk more about the salt bridge at the very end of this video, but right now I'm going to leave it out because I want to make sure that we keep things simple. So this is the basic setup of a voltaic cell. Now, I want to zoom in so that we can see the atoms and electrons in the metal and in the solution and understand what's causing electrons to move along this wire and create electricity. Here's our magnification of the different parts of the voltaic cell. We can see some of the atoms in the metals and in the solutions. So let me show you what's what.
So this is what we've just been imagining in our heads for now, right? We've got the ions, and we're going to see what happens with the electrons.
This is a magnification of the area here. These zinc atoms are on the edge of the piece of the zinc metal.
And what is their charge? The zinc atoms on the zinc electrode, their charge is 0.
And then these Zn2 plus ions are in the solution. They're part of this ZnSO4 solution. I'm not showing the SO4 here. I just want to focus in on the zinc. So zinc ions in the solution and these zinc atoms in the piece of zinc. Then over here, we have these Cu2+ ions that are in the CuSO4 solution. They're dissolved here. And then these copper atoms are on the edge of this piece of copper.
Are we happy with the speed, or do we want to go 1.25? 1.25? Okay. 1.5? We'll try 1.5. We can back off if we need to.
Here, okay? So we've got a wire that connects the zinc and the copper. And we've said that when we hook everything together, electrons start flowing through this wire. Well, why is that? Well, when we connect these two pieces of metal with a wire, it kind of starts a tug of war between the zinc and the copper. They're having a tug of war for the electrons. One of them wins and one of them loses. It turns out that Cu2+, these atoms here, Cu2+ has a really strong pull for the electrons. But then on the other hand, zinc, these zinc atoms, zinc has a weaker pull for electrons.
Yes.
Is this because copper is more electropositive?
Yes. No. Zinc, copper is more electronegative because it's pulling on electrons. Yes, yes, yes.
Well, no, it has a stronger pull for electrons.
So electronegative things pull electrons towards them.
Right.
Yeah? Yeah. Whoops, wrong button. There we go.
So in this tug of war, Cu2+ ends up winning. Let me show you how this happens. So Cu2+ really wants electrons. So it's kind of like it calls over here to zinc, which has a weaker pull on the electrons, and says, hey, zinc, give me some of your electrons. And zinc's kind of weak, so it's like, oh, okay. And what happens is, let's say this zinc atom here gives away 2 of its electrons. And these electrons enter the wire and move towards the copper. Now, when zinc gives away those 2 electrons, it causes its charge to change. It's lost 2 electrons, so it gets a positive charge, and it becomes Zn2+. Now, changing from neutral zinc to zinc 2+ has a big effect on this atom. And that's because neutral atoms make up solid metal, but metal ions usually dissolve in water. So after this zinc atom turns into Zn2+, because it lost these electrons, it's no longer part of the solid metal anymore, and it floats off, it dissolves into the solution. Okay, so that's what happens to the zinc. Then over here, these electrons make their way down the wire to the copper, and one of these Cu2+ ions, which really wants electrons, is going to come over here, and these 2 electrons are going to be added to the Cu2+ ion. Gaining these 2 electrons is going to get rid of that 2+ charge that was on the copper, and that is going to turn it into a neutral atom, which means that it is no longer going to be able to dissolve in solution, and it's going to become part of the solid copper metal here. Okay? So that's what happens to the copper. Now notice that for this whole process to happen, electrons have to move through this wire, and that's where the electricity, the electron movement comes from. Let's see that one more time. So zinc loses 2 of its electrons here. Those move through the wire. Loss of those 2 electrons causes zinc to take on a 2+ charge. It is then going to dissolve in the solution. These 2 electrons are going to move over here to copper, and one of these Cu2+ ions that really wants electrons is going to come, it's going to take them in, and that is going to get rid of the Cu2+. It's going to get rid of the 2+ charge, and this neutral copper atom is now going to become part of this solid piece of copper metal. So that is where this electron movement through the wire is coming from. Zinc loses these 2 electrons. They move through the wire, creating electricity. They come over here, and they join up with the Cu2+, turning it into neutral copper. We have these electrons moving through the wire here, creating electricity. So that is how we get electricity, from these electrons moving from the zinc over here into the copper. And if this happens long enough, we actually see these 2 pieces of metal change, right? Like these zinc atoms keep coming off of this piece of zinc, so it's essentially dissolving. And over time, what we'll see is that this piece of zinc actually starts to dissolve. It gets smaller and smaller. But then on the other hand, those Cu2+ ions are coming out of solution and are attaching to the solid copper. And so they're going to make this piece of solid copper bigger and bigger. And so if we let this voltaic cell run for long enough, we'll eventually see that these 2 pieces of metal actually change size and shape. Here are some diagrams for the process that's happening in the voltaic cell. I want to describe what's going on in terms of oxidation and reduction. So over here, one of these neutral zinc.
So which side is oxidation and which side is reduction? Who's getting oxidized and who's getting reduced? Zinc is getting oxidized and copper is getting reduced. Yes.
Atoms is losing electrons. So that means that oxidation is happening on this side of the voltaic cell. And over here, this Cu2 plus ion is gaining 2 electrons to turn into a neutral copper atom. So reduction or gain of electrons is happening over here. Now, we can give names to these 2 parts of the voltaic cell based on whether oxidation or reduction takes place. So the cathode is the name that we give for the site of reduction, where reduction happens. So reduction is happening here, which means that the piece of copper is the cathode, the site of reduction. And the piece of zinc over here is where oxidation is happening. So the piece of zinc is going to be the anode.
Okay, I don't know if I put that anywhere. Did I? I did. Oh, sort of. Sort of on the next page. Oxidation occurs at the anode. Reduction occurs at the cathode. So if you have something getting oxidized, that is your anode. And that's not going to matter if it's an electrochemical cell or if it's an electrolytic cell. It does not matter if it's a spontaneous reaction or a non-spontaneous reaction. Wherever you have oxidation, that is the anode. And you know what's nice about O and A? They are both what kind of letters? Vowels. Yes? What about C and R? Both consonants. So oxidation occurs at the anode and reduction takes place at the cathode. There's another way of remembering it that I'll let Tyler share with you later. Yes, an ox cared, or sometimes people say an ox red cat. Okay, so you can imagine a red cat. I don't have a diagram of a red cat, but there we are. Okay.
So reduction at the cathode on copper, oxidation at the anode on zinc. Now, let's write reactions for the 2 processes that are happening here, okay? First, let's write the reaction for reduction. We're starting with Cu2+, and this Cu2+ is dissolved in solution. So I'm going to write that with an AQ for aqueous after it to show that it's dissolved in solution. Now, this Cu2+ gains 2 electrons, so I'll write plus 2e-, and that gives us a neutral copper atom. So I just write Cu with no charge after it. That shows that it's neutral. And then it's part of the solid middle, so I write an S after it. So this is the reaction for the reduction process. Over here, the reaction for the oxidation process. We start out with a neutral zinc atom, and this neutral zinc atom is part of the solid piece of zinc. So I'm going to put this S here for solid. Now it loses 2 electrons. To show that we lose something in a chemical reaction, we put it on the other side of the arrow, okay? So I'm not going to write anything right here. I'm going to put this arrow. I'll leave the electrons for last. Losing the electrons turns the neutral zinc atom into a Zn2+ ion, Zn2+, that is now dissolved in solution. So I'll write AQ here. And then finally, to show that I lost those 2 electrons here, I'll put plus 2e- on this side. So this is the reaction for the oxidation. Now these 2 reactions that I wrote, we call them half reactions because each one of them tells half the story of the oxidation reduction process. And we can actually give names to these 2 parts of the voltaic cell as if each one of them is half of the big picture. We call this the oxidation half cell. It's half of the voltaic cell where the oxidation is taking place. And we call this the reduction half cell. It's half of the voltaic cell where reduction is taking place.
So you can fill that in on page 72. Okay. A lot of people, when they first start learning this, they get confused between the oxidation half cell and the anode. Yes? This entire thing here, including the electrode and the solution and everything, that's the oxidation half cell. The anode is specifically the piece of metal. Okay, same thing over here. This whole thing is the reduction half cell. This piece of metal is the cathode.
And it is these half reactions that show what's going on in each one of the half shells, in each one of the half cells. I said half shells. It's like Teenage Mutant Ninja Turtles coming back to haunt me from the 80s. Anyway, we have these 2 half reactions, and we can put them together to get a net ionic equation, which shows the overall oxidation and reduction process. We start with solid neutral zinc and Cu2+ ion, and then at the end of the process, we're left with zinc 2+ ion, and then we have solid copper. This is the net ionic equation that we get from adding together these 2 half reactions. Now, when we're talking about voltaic cells, we're often asked to represent them in cell notation, which is a shorthand abbreviation of the chemical reactions in the voltaic cell. It's a way that we can show what's going on without drawing a picture of the whole thing, okay? Cell notation is
Because drawing the picture, while it is a necessary skill, is a pain in the butt. Yes? Because you're drawing beakers, you're drawing a salt bridge, you're drawing oh my gosh, it gets tiresome.
Sometimes referred to as a cell diagram, just so you know. So here's how we would write what's going on in this voltaic cell using cell notation. We start on the left with the oxidation process, okay? How does the oxidation process start? Well, I have the half reaction up here. It starts with solid zinc, okay? So I will write Zn solid right here. That's how the oxidation begins. Then I put this line here, and I show what we end up with in the oxidation process, which is Zn2+, okay? So Zn2+, and that is dissolved in water. It's part of the solution. It's aqueous. So this shows the oxidation process that happens in the half cell over here, okay? Then,
so we start with the anode. This is nice because it's in alphabetical order. We start with the A, anode, and we're going to finish with the C, cathode. So it's in alphabetical order when we do line notation. And oxidation is occurring at the anode, so we start with the reactant, zinc solid, we put a line, and then we write zinc 2+, which is the product of the oxidation. So we have anode, reactant, anode, product. Next, we're going to have cathode reactant, cathode, product. So what are we going to write next? After the Zn2+, what will we be writing? So we have anode reactant, anode product, cathode reactant, cathode product. So what we have, Zn solid, Zn2+. What comes next? Copper 2+, because that's the reactant at the cathode. Yes, if we look at our cathode reaction, our reduction at the cathode, Cu2+ is the reactant, and our product is Cu solid. So it's our next two things are going to be copper 2+ and then copper solid.
I put two lines like this, and these two lines represent the physical boundary between these two half cells, or you can think of them representing the salt bridge. Okay, now on the right, I put information about the reduction process. So the reduction process begins with Cu2+ aqueous, Cu2+ aqueous, and then I will put another one of these lines, and the reduction process ends with Cu solid. So there's Cu solid. So this is how we can sum up what's going on in this voltaic cell using cell notation.
Now we're just going to pause because I put in my own little whatsie-woo here. Okay. We'll come back to this in just a moment. Yes?
Very likely a stupid question.
No?
But is it on purpose that the states are not subscript there?
Oh, let's.
Yours are really big.
Oh, he just writes them big. That's okay. Yeah, no, there's no particular reason. I mean, honestly, when I make up your worksheets and your tests, I very often don't subscript the states just because it makes them easier to see, especially if I'm doing those like reviews where it's on a half page. The S's and everything get really small and hard to see. All right, so let's just bop here. Where did you go? There we are. Here we go. Standard cell notation. So we have A before C, alphabetical order. We have the anode reactant. And then the product. Then we have the cathode reactant and then the product. So this here is going to be the oxidation. And this is going to be the reduction. Now, what do these lines stand for? A single line stands for a phase boundary. What is a phase? The phase is the state. So you can imagine if we have a metal, which is a solid, that is a different phase than the metal ion, which is aqueous. So we have drawn a phase boundary. Is good? And then the double line represents the salt bridge. Okay, and then we have N plus, which is aqueous. And we have N, which is a solid. So we have, again, we have a phase boundary. For Chemistry 12 and AP Chemistry, this is all you need to know about cell diagrams, okay, cell notation. This is grossly oversimplified, okay? So if you go off to university and you're like, it's not just the reactant and the product, there's all kinds of other stuff happening, because you will sometimes have inert electrodes at which things take place, and the electrode is neither the reactant nor the product, but it does appear in the line diagram. But you don't need to know how to do that. Should you have any desire to learn how to do that, you can go see 6. It says 6.2c, it should say 6.3c. Okay, if you're interested, I don't know, I got carried away, I put something in there. You can go visit Chemist Nate and the Organic Chem Tutor, and they'll teach you about that. But if it were me, I wouldn't really bother. I'd just be like, this is all I need to know for this year, okay? But if you're off at university and you're like, what is this line notation? I'm not understanding my professor. You could go back here and let the Organic Chemistry Tutor and Chemist Nate teach you how to do it. Okay? Is good? Yes. All right, back to Tyler.
We have the oxidation process, and then 2 lines showing the boundary, and then we have the reduction process. So finally, we've talked a little bit about the salt bridge. I said we discuss it at the very end. So let me take a minute or two and explain what the salt bridge is, what it does, and why it's important in a voltaic cell. The salt bridge helps to balance out charge in the voltaic cell. Here's what I mean. The 2 solutions are made up of both positive ions and negative ions. I didn't show the negative ions before. Those are these yellow things. I just showed the zinc and the copper. But along with these metal ions are these polyatomic ions, sulfate, SO4 2-. It's a sulfur with 4 oxygens, and the whole thing has a 2- charge. I didn't want to have to keep using this thing, so I've just abbreviated these as SO4 2-. But the point is, the negative charge from the sulfate balances out the positive charge from the zinc or from the copper. So right here in my 2 half cells, the charges are balanced out. But let's look at what happens as the voltaic cell begins to run for a while.
So we call that charge balance. You can also call it electrical neutrality. Both of that language are used by the AP exam. Charge balance, electrical neutrality, both are okay.
Okay, over here, these zinc atoms are going to give electrons to copper. So they are going to end up with a charge. I'm not showing the electrons here, but electrons are getting sent up here as these turn into Zn2+ ions and as they enter the solution. Now over here, as electrons come over, these Cu2+ ions will turn into neutrally charged copper atoms and attach to the metal. Now look at what's happened to the charge here, okay? Now we have all of these Zn2+, but we have only a few of the SO4 2-. So after just a little while, positive charge really begins to build up in this half cell.
So
and then over here, as the
circle.
positively charged ions, like this, lose their charge by gaining electrons and turn into neutrally charged copper, now there are a whole lot more SO4 2- than there are Cu2+.
So you can fill in those circles on page 74.
Negative charge begins to build up on this side. And if this positive and negative charge build up too much, the cell can't run anymore. It can't continue to make electricity. So
How do we fix this problem? What do we add? A salt bridge.
that is where the salt bridge comes in. Let me get rid of this wire and show you what the salt bridge looks like. Here is the salt bridge. It is a tube shaped like an upside down U that, in our case, is filled with sodium chloride. And you can see the Na+ and the Cl- ions. Now, at the ends of the salt bridge, there are cotton plugs, a little bit of cotton there.
Fill in cotton plugs. Everyone always forgets the cotton plugs. Okay? You can also call it a porous plug.
And the cotton prevents the solution from just pouring out into the half cells. But these ions are able to slowly pass through the cotton plugs, and here's what happens. We said that negative charge is going to start building up in the half cell over here. And so the positively charged Na+, is going to begin moving over into this half cell to help balance out the charge.
The positive charge is attracted by the negative charge that is being produced there, yes? And so those positive ions move towards any negative charge buildup, making it, once again, neutral, maintaining the charge balance, maintaining electrical neutrality.
So the Na plus ions are going to begin moving in this direction to balance out the negative charge. And over here, we said that positive charge begins to build up. The Cl minus ions are going to begin moving through the salt bridge to come out through the cotton and help to balance out the positive charge that builds up on this side of the voltaic cell. So over time, what we're going to see is we're going to see that the Cl minuses move in this direction to balance out the positive charge that builds up here. And then we'll see that the Na pluses begin to move to this side to balance out the negative charge that builds up here. A salt bridge helps to balance these charges to make sure that they don't build up too much, and that would prevent the voltaic cell from being able to work. Wow, so we just learned so much about galvanic or voltaic cells. Okay, so here's the basic structure of a voltaic cell. We have the zinc sulfate solution here, copper sulfate solution here, we have zinc metal and copper metal. Now, when we hook this all together,
this picture is on page 79. I put some other stuff in between, but this is on the summary page on page 79. Whoops.
Electrons start flowing from the zinc to the copper. And that's because copper that's in the solution has a strong pull for electrons, whereas the zinc has a weaker pull, so the copper wins. As electrons move from the zinc to the copper, they are lost in the zinc, so oxidation takes place, and they're gained here in the copper, so reduction takes place over here. We call this the oxidation half cell, and we call this the reduction half cell, because oxidation is happening over here. The piece
Well, what happens to the ions to the salt bridge when it goes in?
Probably your other solutions will run out first. Basically what happens is, you know how you've got copper 2+ over here, right? You're probably going to run out of copper 2+ ions before you run out of ions in the salt bridge. Also, the zinc ions that are produced, they're also positive ions, so they're going to migrate through the salt bridge also towards the copper electrode. So if you've got sodium in here, sodium's moving this way, zinc is going to come out and zinc's going to move. That way, eventually some zinc ions will end up over here. That's going to take a long time. But yeah, it does happen. And same thing over here, negative ions, if you've got some sulfate ions, they're going to start moving up into the salt bridge and moving over to the other side as well. Yes? It is the archetypical cell. I don't know. I guess zinc and copper are pretty easy to come by. I mean, it's hard to make a gold-silver half cell. That's expensive. You know what I mean? So, and they're relatively non-toxic, although copper's toxic. So I don't know. I don't know why it's the cell. It's a good question.
piece of zinc is the anode, because reduction is happening over here. The piece of copper is the cathode. Then finally, we can write half reactions for the two processes that are happening in the different half cells. Here is solid zinc losing 2 electrons because they're moving out to turn into a zinc 2+ ion, which is going to enter the solution. And then over here, Cu 2+ ion that's in the solution gains 2 electrons and turns into solid copper. It's going to attach to this metal right here. And then finally, we can sum all of this up by writing this, this cell diagram or cell notation, which shows everything that's happening in a shorthand abbreviated form. Zn solid, then a line, Zn2+ aqueous. This shows the oxidation part. Then we have these 2 lines representing the salt bridge or the boundary between these 2 cells. And then we have the reduction part, Cu2+, line, giving us Cu solid. So that is how a device like a galvanic or voltaic cell uses a chemical reaction to create electricity.
Okay. Now, just before we finish up with this, we have, here we are. We're just going to take a look at a couple other things here. So, things to take note of. The reason the cathode is called the cathode is because that's where the cations migrate to. That's the actual reason it's called a cathode, is because that's where the cations go towards. Okay, so which direction do cations go? Cations go towards the cathode. So that's something you need to know. You can figure it out. You can be like, oh, the anode is oxidation, so I'm losing electrons, so I'm making more positive charge. So the positive charge is going to want to move away from the anode and towards the cathode, which is gaining a lot, like, yeah. So you can use any one of these to figure out the other, but it can be nice just to have them on the tip of your tongue. One of these things can remind you of all the others. So anions move towards the anode. Why are they doing that? Because the electrons are leaving the anode, which means we need more negative charge on that side. So the anions are going towards the anode. You'll notice that the sulfate here is going towards the anode. It actually will kind of move towards the anode. It won't react because it's not really electrically very reactive, but it will move towards the anode. The zinc will actually move up into the salt bridge and move towards the cathode because the cations move towards the cathode. Sodium in our salt bridge will move towards the cathode. Okay, the copper moves towards the cathode and then it actually gets reduced. So all the cations are eventually making their way over to the cathode. All of the anions, including the sulfate on this side will eventually make its way up in there. The nitrate, that's part of the solution we put in the salt bridge. All of those negative ions are all moving towards the anode. Okay? Here's another way to think about it, but do not explain it on the AP exam. They will not accept a salt bridge completes the circuit. That is not an acceptable answer. That's been in the chief reader's report. However, for my own mind, like it just makes sense to me. I'm like, I only have like a half circle here, right? And everything gets stuck. Here, I'm completing the circuit, but don't write that. I should have not even put it in there, but you know, whatever. And don't forget, if you have electrons flowing in one direction, the anions will flow in the same direction. The cations will flow in the opposite direction. All negative charges all flow in the same direction. So if the electrons are going counterclockwise, the anions will go counterclockwise and the cations will go clockwise. Okay. Alternatives to a salt bridge. Yes. Yeah. A porous barrier. So you might put in a porous membrane separating one from the other. This would preclude you having to have two beakers. You could have one beaker with a porous barrier. So you have a porous membrane or a porous barrier that separates the zinc solution from the copper solution. You could have, they do have beakers that are set up like this. They've made the glassware. So there's a porous disc in there and they're just kind of attached. It's kind of funky. I only put these in here because you will see cells drawn like this sometimes and you'll be like, what on earth is happening? Yes? What this allows for is it allows for the passage of ions from one side to the other to maintain that electrical neutrality. Do you remember the paper towel? You can use a piece of filter paper, just like you remember for our chromatography lab. Do you remember that one? Where we put the little dots of color and it, yeah. Okay, so that's basically what's happening here. Okay, and the ions will travel through that paper towel or filter paper. And finally, there is actually such a thing as a porous cup. So it's made of like sort of ceramic with little pores in it. And you would put the copper solution into that side and leave the zinc on the outside. If you are interested more in learning more about cell notation, it is here. Okay. I think what I would actually like you to do tonight is to do 6.3D. You're going to walk through 6.3D with Mr. Colger. It's only 10 minutes. 10-minute video. How are you doing with, like, does that seem like enough, or could you do the questions at the end of 6.3b as well? What? We're good? 6.3d is good? Okay, good. Here we go. Thank you.
It's not gonna take that long. It's more, no, we should do that first or only that. I have, thank you. You already okay. Can you drive more than one person?
But if I go in depth, everyone will.
Like separately.
Not sure if I missed the point, but I don't understand why it's such a big problem for big buildup of positive charge.
Okay, what does negative do to negative?
Negative, so it just caused an explosion. Is that the problem?
Well, the thing is, it can't, because things flow to the lowest potential energy state.
Right.
If you're putting negative beside negative, that's a high potential state.
Right.
So they simply won't move together.
Oh, so they
because
just not
they're happy
they're
where
gonna
they are.
stop
They're
moving.
just going to be like,
They're just gonna
"Ooh."
stop moving.
Yeah.
Because the negative charges are going to repel so much that they're not going to be.
They're not going to be able. They're not going to be like, "Oh, I'd like to go over there, but I can't
Right.
because then I'd have a buildup of charge." Yeah. Yeah.
I don't want people definitely be a better secure than me.